So the law of universal gravitation predicts that all masses are attracting each other. Kind of a strange idea that seems to say that everything should get pulled towards each other. But as we learned when we studied circular motion, if an object has some sort of a speed and a force is exerted somewhat perpendicular to it, and if it's not in the same direction as the object's motion, it's going to cause that object's motion to change in terms of the direction. And if these two things are really just perpendicular to each other, okay, if you have that sort of perfect situation, then the path that the object follows is a perfect circle. And so that's actually the assumption that we will make, is that we do have this circular path. It is an assumption, it is an approximation, but there are lots of situations in the universe that are very close to this. Everything out there is moving, and so this gravitational force is not just causing everything to slam into each other. It's causing the direction of objects' paths to change. And in many cases, that path ends up being a circle or a near circle. And so this is a useful part of, or application of, gravity to study. Two things that we will derive within this video is the speed of this sort of satellite, and then also the period, the time for one rotation for that satellite. So the speed of a satellite that's moving along a circular path is found by using this formula here. Probably should say P here for like planet or something, but it's the square root of that universal constant g times the mass of the bigger object, the planet, divided by r, and the square root of all that. So let's kind of give ourselves a visual here. Imagine that we have some sort of larger object like a planet, so we'll call that m sub p, and we have a smaller object that is moving, so that its velocity is perpendicular to this direction here. So this is our r value between the center of the planet and the center of our orbiting object. And if those two things are perpendicular to each other, then our object follows a circular path. Okay, and again, we're going to kind of focus on that approximation in this video. All right, so if that's the case, there is simultaneous gravitational forces being applied to these two objects, our planet, and then we'll call this m sub s for our satellite. But the gravitational force has a bigger effect on the satellite. The actual values of the forces are exactly the same. Okay, I'm going to draw my red arrows here the same length. But because the mass of the planet is so large, the effect of that force is very small. And so it kind of moves around in a little bit of a circle, but that circle is within the planet itself, and so you don't really almost notice it. The smaller mass of the satellite is really affected by this force, and so its motion is really affected, and you see the circular path from our perspective. All right, if that's our only force that we're really dealing with, the gravitational force, that is the inward force. And so when we think about Newton's second law, F equals ma, the only force that is on the left-hand side here is the gravitational force, and it points inward. So the gravitational force would be capital G, that constant, times the mass of the planet, times the mass of the satellite. Okay, it's this attractive force between these two objects. Because it's perpendicular, though, it causes the mass of the satellite to have an inward acceleration, v squared over r. And these r's are the same in this case because the circular path exactly matches, the radius of that circular path exactly matches the radius or the r distance between the two objects. Sometimes that changes, we'll see that a little bit later. But taking a look just algebraically now at my equation, I can see that the mass of the satellite cancels out. We'll talk more about that in a little bit. I can see that one of my r values can be canceled, can be multiplied by r and have those removed. And so here I have my formula that v squared is equal to capital G m times, or m of p, the mass of the planet, divided by just r. And then when I square root both sides, I get that v is equal to the square root of gm over r. Again, make sure you recognize that this m is the mass of the planet, not the thing orbiting. R is the distance between the two objects, also the radius of the path. And what we are finding is the speed, the linear speed of that satellite. So a second derivation that we need to be familiar with is how to find the period of a satellite. Recall that the period is symbolized by a capital T rather than a lowercase t for just a regular time, and that it's the time for something to make one complete cycle. And so in this case, it would be the time to go once around that circular path. So if we want to relate the period to the speed we just calculated, this object would be moving at a constant speed, and so its speed would just be distance over time, or circumference over capital T. Some people like to think about this in terms of angular speed. This formula, omega equals 2 pi over t, is directly on your formula sheet, and you can transform that into what I originally wrote by multiplying both sides by r and recognizing that r times omega is v. So if you don't really remember this formula, that's one way of sort of getting to that, since the derivation of this is important. But back to this, if I recognize that something moving in a circle is going to have a linear speed of 2 pi r over t, I can set that expression equal to the formula we just derived, that for a satellite, its speed is the square root of capital G times the mass of your planet divided by r. All right, so how do we get to one of these formulas then? How do we express this in terms of the period? This is just algebra. I would tend to square both sides of the equation. So 4 pi squared r squared over t squared. And then over on this right-hand side, the square root just drops. And then if I want to get t by itself, one thing I can do is to just solve for t squared. So I'm going to cross multiply this way and get 4 pi squared r cubed. They don't cancel, they combine to make r cubed. And then I would get t squared times g capital M, but then I would divide by capital G capital M. Okay, so that's one way of expressing the period of the motion. Another way is just to square root. And so this is really just a preference, which way you like to write this. I guess we would square root, so we would get rid of some of this. So the square root of 4 is 2, square root of pi squared is pi. I could either write this as the square root, or the the square root of r cubed, or r to the 3 halves, and then over gm. Okay, so that gives me the top version. One of these two you should be familiar with. A lot of times too, all you really need to notice is that the square of the period is linearly related to the cube of the r. That's an important idea. What turns out not to be important, though, is the mass of the satellite. In all of these derivations, the mass of the satellite, m sub s, cancels out, and so it doesn't matter. That's interesting, really, when you think about it. So if I were orbiting around the Earth, okay, so if this is the Earth, and here's me orbiting around the Earth, going around, hopefully in a spaceship or something like that, my speed and the speed of the spaceship, they're going to be the same. They're going to be this value right here if everything is orbiting together. And that's actually what produces that sort of feeling of weightlessness, is the fact that everything moves together and in fact has the same acceleration towards the center. And so it feels as though, as if you were just falling, just like an object, if it has no none of that tangential speed, if it's really just falling, then it feels weightless. We say that if gravity is the only thing acting. If it has some sort of forward motion as well, and if gravity still is the only force acting, it's still going to feel weightless, because the only force is gravity. So whether the object has speed or doesn't have speed, that feeling of weightless, or what I like to call normal forcelessness, is going to be there. And so that's why normal forcelessness, yes. So that's why, astronauts that you see in videos and so forth, they do sort of float around as if there was no gravity. It's not that gravity is that much smaller. Usually on a satellite, the value of G is around like 8 meters per second squared. Okay, it's not that much smaller. It's just because everything is experiencing that same gravitational field strength, and so it's really as if it's just falling towards the Earth.